Greetings. In this video I'll show you how I built a digital phase converter with some relatively simple components that can run industrial machine tools like this one behind me without any modifications or issues.
If you don't wish to understand the reasons for the components selected or how any of it truly works, skip to 10 minutes and 37 seconds to see the converter system schematic and finished results. Please also take this time to read this very important disclaimer. We recently moved factory locations, and this location happened to not have three-phase grid power. In order to obtain such a utility, in our case, was going to be in the range of 6 figures. That entails bringing in a new transmission line from the closest substation, a new transformer, and all the groundwork that goes along with such a big task. Not to mention the lead time would have been very long, in the range of 3 to 6 months. That's okay if you can justify that with your business plan, but for what I'm doing right now, that simply isn't economical. So with that being said, let's start at the beginning of the conversion system. Our new factory has a TT electrical installation. There are a few main types of these, and they matter quite a bit for this application and must be understood. In this schematic, you can see there are 2 phases coming from the substation on the existing transmission line. These will be at around 11 kV and they go into a step-down transformer on the pole. They look like the one shown here in the schematic. This reduces the voltage to around 240 volts and provides us with a neutral and an L1 connection. This is also commonly referred to as the live or hot conductor in America. In our case, we would be able to get another phase from the existing transformer at a much lower cost, which will effectively double our current capacity. It will also allow us to have a higher incoming voltage if needs be. Perhaps upsizing the transformer is also possible. These are avenues we will look into, and I will probably make a separate video on that topic. The neutral conductor is also then referenced to earth via an earthing electrode located on the transmission pole. This is supposed to make a low resistance connection to the ones located around the building, but your results may vary on a lot of factors, which is why modern standards have since switched to a direct bond at your main incoming fuse, like a TNCS or other electrical installation system. The devices used to create 3-phase will need a good earth connection, or else you will get undesirable results such as voltage and frequency instability. A certified electrical contractor can come and test your earthing setup and see if it conforms with the standards. I installed a new earthing rod array for the building and it was certified within 22 ohms. Anything below 100 ohms is permitted for a TT install, but with a TT or any system that uses an earth rod as the main earth reference, you will not be able to carry the full fault current back to the transformer's start point. You ideally need an RCD protection with a TT system for safety, and I would recommend strongly RCD protection regardless of your electrical system. Finally, we have surge protection. These are installed in your main and sub consumer units as specified and required. They protect you from dangerous voltage transients that can damage your equipment. I highly recommend installing these before and after your VFD to protect from any damage that may happen. Once those basics are all established to protect you and your equipment, we can move on to actually building the converter system. I will have a supplementary video going over all of the types of converter systems, how they work, what you should and should not use them for, as there are some major pitfalls that you can make that will cost you a lot of money. Anyway, the basic principle of this is a variable frequency drive that has been customized slightly, some line and load reactors and filters, and a sine wave filter. If you wish to have a neutral or a proper ground reference voltage for electronics, like used in CNC machines, etc., you will require a delta to Y isolation transformer. It must be an isolating type transformer. That is very important. The modifications mentioned to the VFD are quite basic, but are important. VFDs of this size, mine being 22 kilowatts, usually are all 3-phase inputs. You'll have to ask the manufacturer if you can run them on single-phase supplies. mine can be without a problem. Then inrush currents. There are a lot of misconceptions like how a VFD can't just switch a load. That may be true with certain types, but that's generally not true for all of them. However, it is recommended to ask your manufacturer what type of current spikes you can draw. You can also add some capacitors to the DC bus to provide it with higher starting current capabilities. But again, it is highly recommended to take these up with the manufacturer of the drive, as they can advise you best on this application. Prior to anything in the system, these two items will be installed. They will prevent any items being damaged on your line supply and the surrounding area's line supply. Without them, you will have essentially accidentally created an EMP-like weapon, which can stop devices like Wi-Fi and satellite systems from working properly. That is simply because a variable frequency drive is inherently a very noisy device. Switching thousands of times a second can generate a lot of RFI on the line supply. The reactor also has another use in the system, as it can smooth the current waveform, preventing big load spikes that can take out light bulbs and other similar devices. The drive will be running in a static mode where it's providing 400 volts 50 Hz from the output terminals constantly. This is going to be a PWM or pulse width modulation signal and is useful for nothing more in this application other than controlling permitted motors. It is then going to go into a sine wave filter, which is essentially a big inductor with some capacitors. This will create a more sinusoidal waveform as a result from line to line, but when referenced from ground, it is completely wrong. You can see here the purple trace is the line to line waveform, and this is fine for machines such as
this machine. You can immediately see this electrical cabin behind me has no electrical sensitive devices, control circuitry, or anything of that nature. Instead, it just has basic contactors, transformers, motors, that type of thing. This is not a problem if you want to run this type of machine. Many machines like that one will work without a problem, but where power quality is critical, you need some additional components to clean up the signal, so to speak, like for this white erosion machine behind me. You can immediately see the contrast between these two machine tools and how they function. There are a multitude of control electronics, inverters, drives, and process monitoring circuits in here which are referenced to ground and require a high quality of power to function without breaking down.
This is where the isolating transformer comes into play. Not only can it electrically isolate the VFD side, which has its benefits, it can provide you with a neutral and proper ground referenced lines, which are vital for CNC machine tools and sensitive devices. Then from the transformer, that goes into a final RFI filter, then to my distribution board, which has surge and all relevant protections for the machines that I'm using.
You might have thought we were done with the system, but something called regenerative current can be injected back onto the line supply from inverter systems such as the Drive 611 as shown behind me, or newer schematic systems. Even FANUC systems can do this these days.
That can cause problems even in some real supplies, where there are no additional loads to take up that current. But an even bigger problem is that our line supply happens to be this converter system. When that regenerative current enters the line, it raises the voltage of the VFD's DC bus and causes an overvoltage alarm. The one that I have maxes out at 800 volts DC. Now, nothing can actually be damaged when this happens due to the protections being put in place by the manufacturers. It will literally just shut off, closing the related contacts, and that's it. So, what can be done about this? You can contact your drive manufacturer and ask for a DC bus clamping transistor or similar. It monitors the DC bus voltage, and when it exceeds the safe level, it will send excess energy into the braking resistor to be converted into heat, preventing the overvoltage before it even starts. If your manufacturer doesn't make such a product, which would be very unlikely, there are a few companies who make their own version which will work on any VFD that has its DC bus terminals accessible. A company based in the US called Bonitron makes some great looking products for this application, and it's most likely who I'm going to go to for my solution. They make an external braking transistor which will clamp the voltage at a set level and prevent overvoltage alarms, thus allowing any machine with regenerative current capabilities to run without fail. Here is the detailed electrical schematic of my system with component values. This of course can be scaled down and up. You can download this schematic PDF from my website's community page, link in description. If people are interested in this system but don't want to build it themselves, I can build that for them if there is interest in that service. This video is for the people who want to DIY and learn about phase conversion in a truly transparent manner. Future videos will go over all types of systems, the final electrical enclosure design with networked process monitoring and safety features. Stay tuned for that. So with that being said, let's check out some results running from this exact system.